In this lesson, we are going to look at the purpose and operation of the artificial horizon, or the attitude indicator as it is often known. And we will also look at the different types of artificial horizons and their associated errors and/or advantages. The artificial horizon, or AH, is also known as the attitude indicator, or AI, and it is the primary attitude instrument in an aircraft. It provides the pilot with information in terms of the aircraft's attitude, both in pitch and roll. We can see an example of a mechanical instrument display on the left, and on the right we can see a more advanced electronic display. The basic information displayed, however, is essentially the same. A mechanical instrument display consists of a gull wing motif attached to or etched onto the instrument glass. The gull wing motif will therefore move with the aircraft in pitch and roll. Appreciating this fact is fundamental to reading the instrument. Behind the glass is a horizon bar or image, which is attached to or linked to an earth gyro, which stabilizes the horizon image in the earth horizontal. An earth gyro has its spin axis XX tied to or maintained in the vertical by the Earth's gravity. And in this diagrammatic representation, we can see that the gyro rotor is attached to the inner gimbal, whereas the outer gimbal will be attached to the instrument case. The way it works is that if the aircraft should now pitch up, the outer gimbal, which is in effect attached to the aircraft, and therefore the gull wing motif, will rotate about the axis YY. A guide pin protruding from the vertically stabilized inner gimbal forces the horizon bar down. The movement is magnified by the length of the horizon bar arm, indicated here. And the result is that the horizon bar is now below the gull wing motif, and the indication on the instrument is that the aircraft has pitched up. In roll, the aircraft, and therefore the instrument case and the gull wing motif, will rotate around the ZZ axis, while the gyro and the attached horizon bar will remain stabilized. The result is that the instrument shows a roll in the direction of the bank. The amount the instrument case can move relative to the gyro is limited by fixed stops to prevent internal damage. In older designs, the limits are plus or minus 60 degrees in pitch and 110 degrees in roll. In modern designs, there is complete freedom in roll, and up to plus or minus 85 degrees in pitch. Use the mouse to move the pitch and roll control to see the effect of pitch and roll on the instrument indications. The degree of bank is indicated by the marks on the upper arc of the display. The first 3 marks on either side of centre are in 10-degree increments. The next long mark denotes 60 degrees of bank. The earth gyro in the artificial horizon or attitude indicator may be air-driven or electrically driven. Let's look at the air-driven version first, and the errors associated with it. In the air-driven artificial horizon, the spin axis of the earth gyro is tied to the earth vertical by a system of pendulous vanes and air jets. Any tendency for the gyro to topple is counteracted by the precessed reactive force from the air jets. The centre of gravity of the gyro is also kept below its pivot point on the inner gimbal to assist in keeping the gyro vertical when not in use. Let's look at how it works in more detail. If we look at a diagrammatic view of the gyro and rotor housing, we can see that at the base of the rotor housing there are 4 air exhaust ports. Each port is partially covered by a pendulous vane, which we will call A, B, C, and D. air is exhausted through the partially open ports, and when the gyro rotor is vertical, the air being exhausted through the ports will be of equal and opposite pressure. However, should the gyro rotor axis wander from the vertical, the pendulous vanes on opposing sides of the rotor housing move, so that as one vane closes, the other one fully opens. In our illustration here, the gyro rotor is toppling, and we can see that by gravity vane B has closed, while vane D has fully opened. The result is that the air pressure escaping through the opposing port D will no longer be balanced, and the excess reactive force is precessed through 90 degrees in the direction of rotation of the rotor to re-erect the gyro. Note, it is usual for air-driven gyros to rotate in an anti-clockwise direction when viewed from above. These gyros are known as classic gyros. The error associated with the air-driven artificial horizon is that the pendulous vanes and the weighted rotor base will be affected by any acceleration, not just that due to gravity. A straight line acceleration will result in a nose-up pitch attitude and a right wing low indication. In flight with sole reference to instruments, this can be misinterpreted by the pilot as an indication of a climbing right turn. Let's look first at why we get a false pitch-up indication, and then we will look at why there is also a false right-wing low indication. The false pitch-up indication results from the effect of inertia on the lateral pendulous vanes. During an acceleration, the lateral vane on the starboard side lags, which opens the starboard exhaust port, while at the same time the port side exhaust port closes. The reactive force is to the port side, but is now precessed 90 degrees in the direction of spin, towards the tail of the aircraft. This causes the rotor housing to move backwards and indicate a false pitch up. Let's look now at the reason for the false right-wing low indication. The false right-wing low results from the effect of inertia on the mass of the rotor housing, which, as we know, is designed to place the centre of gravity below the rotor assembly pivot point on the inner gimbal. In other words, it is bottom-heavy. During a straight and level acceleration, the heavy base of the rotor housing tries to lag. However, this force will be precessed, which results in the rotor housing moving to starboard. If the rotor housing moves to starboard, the whole gyro assembly will tip to port. This gives a right wing down indication, or in other words, a turn to the right indication. To understand this, just remember that although the gyro assembly has tipped towards the port wing, the gull wing motif in this case has remained earth horizontal. If we think about it, and imagine we are flying on instruments in zero visibility, the false right-wing low indication can be visually interpreted from the instrument as a right turn indication, because of the movement of the horizon bar relative to the gull wing motif. Errors will also arise as a result of a turn. A turning manoeuvre is in effect an acceleration, but this time the acceleration is towards the centre of the turn, resulting in a horizontal force component. Centripetal force, acting in this instance on the fore and aft pendulous vanes and the weighted rotor housing, will combine with the vertical effects of gravity to give erroneous indications in pitch and roll. The magnitude of the errors in both pitch and roll will be complex and will vary with the speed and the rate of turn. For a chosen speed and rate of turn, it is possible to compensate for these errors by tilting the top of the rotor axis slightly forward and slightly to the left. However, if we consider an uncorrected classic gyro, that is, an air-driven gyro rotating anticlockwise when viewed from above, the following errors will occur. Turning through 90 degrees, the instrument will underread the bank angle, and the pitch error will cause a false nose-up indication. Turning through 180 degrees, the bank angle will read correctly, but the pitch error will still result in an erroneous nose-up indication. Continuing the turn through 270 degrees, the instrument will now overread the bank angle, while the pitch error still causes a false nose-up indication. Turning through 360 degrees, the bank angle will read correctly, and the pitch angle will be correct. To summarize turning error then, any error effect will depend on the magnitude of the turn, and the magnitude of the error will depend on the speed and rate of turn. The error will apply equally to a turn in either direction. Let's look now at the electrically driven artificial horizon. The basic principle of the instrument is the same as for the air-driven horizon. However, in the electrical instrument, the earth gyro is controlled by mercury leveling switches and torque motors, instead of a system of pendulous vanes, and the rotor usually rotates in a clockwise direction. The way it works is that the mercury switches activate pitch and roll torque motors, which precess the gyro back to the vertical as soon as it starts to wander. There are two leveling switches, one to sense pitch and one to sense roll. We can see the principle of the mercury switch here. The switches are fixed to the base of the rotor and rely on gravity to centralize the mercury between two open electrical contacts. If a leveling switch is not level, the mercury will move to close the electrical circuit which will drive its associated torque motor. Because of the 90 degrees precession rule, the torque motor on the side of the inner gimbal corrects wander in the rolling plane. That is, it applies torque around the lateral axis to produce rotation around the longitudinal axis. Likewise, the pitch torque motor is on the outer gimbal, so that the precession is around the lateral axis to correct for pitch. So a point to bear in mind is that the mercury switch which senses wander of the spin axis in the fore and aft plane has its associated torque motor fixed to the outer gimbal. The mercury switch which senses wander of the spin axis in the lateral plane has its associated torque motor on the inner gimbal. Advantages of the electrically driven artificial horizon or attitude indicator over the air-driven instrument are: firstly, there is greater rigidity, due to the higher spin rate possible, which in turn will give a low precession rate. There is less potential, therefore, for the gyro to move out of Earth vertical, and so more accuracy can be achieved. Secondly, a fast erection system can be incorporated, which can erect a toppled gyro at up to 120 degrees per minute, compared to the normal rate of 4 degrees per minute. Thirdly, as there is no requirement for a heavy erection chamber and pendulous vane system, acceleration and turn errors are eliminated or reduced. As we have seen, acceleration errors are minimal in the electric artificial horizon. However, there would still be a tendency under acceleration for the mercury in the mercury switch to close its electrical circuit as a result of inertia acting on the mercury. This would result in the pitch torque motor falsely precessing the gyro assembly out of vertical. So to overcome this, a secondary pitch cutout switch is incorporated in the circuit, which activates when an acceleration of 0.18 g or greater is experienced. Similarly, in a turn, the mercury in the mercury roll sensing switch would falsely activate the roll torque motor. A secondary roll cutout switch is therefore incorporated in the circuit, which is activated at 10 degrees angle of bank. Let's look now at a further development of the gyro horizon, known as the vertical gyro unit. The vertical gyro unit can also be known as the vertical axis gyro, the remote vertical gyro, or the vertically axis data generation unit. In the vertical gyro unit, the gyro is a remote gyro, which operates a synchro system to generate and transmit attitude signals to a steering computer and to an amplifier unit. After processing and amplification, the signals are transmitted to servo units within an attitude director indicator, or ADI, and also to control channels in an auto-flight control system, or AFCS. The vertical gyro, its leveling switches and torque motors are essentially the same as in the electrically driven artificial horizon. Whenever a change of aircraft attitude occurs, signals flow from pitch and roll synchros on the relevant axes of the vertical gyro to the corresponding synchros within the indicator. Servo motors rotate to position the pitch bar and the horizon disc to indicate the changing attitude of the aircraft. The principle is the same for an electronically generated ADI, and diagrammatically we can see the essential inputs here. The image of the ADI is generated by a colour cathode ray tube, or liquid crystal display. The system is advanced, not only in terms of physical construction, but also in the extent to which it can display attitude and other relevant information. The Electronic Attitude Director Indicator, or EADI, is looked at in detail in the lesson on the Electronic Flight Information System. Locating the gyro unit in a remote location has advantages. The principal advantages are firstly that a larger gyro unit can be used, as the unit can be located away from the flight deck. A larger gyro will give greater rigidity, and therefore less precession and more accuracy. Secondly, a very high gyro spin rate can be achieved, which again gives greater rigidity and therefore less precession and more accuracy. And thirdly, electronic signals can be easily used to provide information for flight director and auto-flight control systems. This concludes the lesson. A summary of the main points of the lesson follows. The artificial horizon, or AH, is also known as the attitude indicator, or AI. The AH is the primary attitude instrument. It provides information on the aircraft's attitude in both pitch and roll. The display consists of a gull wing or similar motif, which will move with the aircraft in pitch and roll. An Earth gyro stabilizes the horizon image in the Earth horizontal. The Earth gyro in the artificial horizon may be air-driven or electrically driven. In the air-driven artificial horizon, the spin axis of the Earth gyro is tied to the Earth vertical by a system of pendulous vanes and air jets. A classic air-driven gyro rotates in an anti-clockwise direction when viewed from above. The pendulous vanes and the mass of the rotor base will be affected by acceleration, resulting in a pitch up and right wing down indication. A pitch up and right wing down indication due to acceleration gives an erroneous indication of a climbing right turn. The pitch up indication results from the effect of inertia on the lateral pendulous vanes. The false right wing down indication results from the effect of inertia on the mass of the rotor housing. The effect of turning errors will depend on the magnitude of the turn, and the magnitude of the error will depend on the speed and rate of turn. Turning error will apply equally to a turn in either direction. The basic principle of the electrically driven artificial horizon is the same as for the air-driven horizon. In the electrical instrument, the earth gyro is controlled by mercury leveling switches and torque motors. The mercury switch, which senses wonder of the spin axis in the fore and aft plane, has its associated torque motor fixed to the outer gimbal. The mercury switch, which senses wonder of the spin axis in the lateral plane, has its associated torque motor on the inner gimbal. The advantages of the electrically driven AH should be remembered. The advantages of the remote vertical gyro should be remembered.